So, correlation, covariance, and what we'll call the simple regression, of course, what we'll call the simple regression model. (14.2), the simple regression model. The correlation coefficient tells us the correlation between two variables. It tells us the direction and the strength of the relationship. Remember, some variables, as one goes up, the other goes up. Typically, the higher, the taller people are, the more they weigh. Positively related. Some variables are negatively related. The more beer I drink, the worse I'll do on my test. Negatively related. Number of beers goes up, test score goes down. Some variables are not related at all. There is no relationship. The correlation coefficient is close to 0. There's no correlation coefficient between shoe size and test scores. None. To do math on this, we'll start doing what we call regression analysis. Remember that when we did our scatter plot, we then fit a line to this using the ordinary least squares method that we called a regression line. That's the line of best fit to this data that we called a regression line. With regression analysis, we assume that one variable, called the response variable, is influenced by others called the explanatory. Your book calls them response and explanatory. I will use that from time to time. But I will use terms that are more commonly used in statistics. I will use dependent and independent. Dependent variables and independent variables. I will, at one point or another, screw up these two and mix them up. You should call me out when I do that. I'll also, at some point, mix up Medicaid and Medicare, even though I work for a living in Medicaid. Your dependent variable is what we want to forecast. Your dependent variable depends on your independent variables. If what we're trying to predict is test scores is our dependent variable. And we're going to predict it based on how many beers you drink per week. Your number of beers doesn't depend on your test score, usually. It might. I got a really low test score, I'm going to drink more beer. They're still negatively correlated. We're going to use dependent and independent, as most books and most statisticians do. Using regression analysis, we can predict the response, we can predict our dependent variable, given values for our explanatory. So, thinking about projects, you might want to predict sales of something based on any number of variables. Unemployment rate, GDP, median income, weather. Aaron, that's crazy. You can't predict sales based on the weather. Yes, I can. I've done it. Give me GDP and the unemployment rate and the average number of sunny days, and I'll get real close to telling you how many leaf blowers you're going to sell. Give me that and I'll get real close to telling you how many snow blowers you're going to sell. Give me a number of days that there's snow and I'll tell you within 10% how many snow blowers you're going to sell. I've done it. It's a project I've worked on. Refrigerators, cars, computers, we can predict all these sales. Think about your projects. It's pronounced stochastic. Stochastic. If our response variables matter, if there is a relationship, we say that it is deterministic. that that variable has predictive power. It's a good variable. It's useful to us. It has some predictive power. It is deterministic. If we find that the relationship is inexact, a relationship is stochastic. Shoe size and test scores. No relation, stochastic. Sunspots and test scores. Sunspots in anything, really. In regression, we always include an error term for that which we don't know. Random error. Things we haven't considered yet. Is every bit of snowblower sales based on snowy days and GDP? No. There's always some variation. I'm never going to get perfect. I'm never going to perfectly predict snowblower sales. So, there's always some error. We always include an error term. Here is your simple regression model. Simple linear regression model. Write it down, underline it, circle it twice, then highlight it. Y equals beta sub 0 plus beta 1 x plus an error term. Write it down, circle it, highlight it, put those little sparkly lines out from it. It's your bread and butter. Y is what we're predicting. Y is our dependent variable. Beta 0 is our intercept. Beta 1 is our slope. And a random error term. What does this look like? Yeah, if I take this out, what does it look like? It looks like our own formula for the line slope-intercept form, doesn't it? Because it is. This is just our random error term that says, we know that there's some error and we're not sure what it is. It's just, yeah. Remember your first semester of calculus when you're doing derivatives and we take the derivative and what do we tack on to the end of the derivative? Plus c. Do we ever know what c is? No, we just know that there might be a constant out there. Because the derivative of any constant is 0. The slope of a straight line is 0, so the derivative of that is 0. So we know that there might be a constant out there, so we tack on the c at the end. We tack on our epsilon up here. We know that there's an error term out there. Because when we calculate this, this is our regression equation. When we fit data, this is our regression equation we actually use. We don't do math on the error term yet. You know how we read this? Y hat. It's got a little hat on it. It's my favorite thing about statistics. It's got a little hat on it. You know what we call it? Y hat. You can go to Y hat on Twitter. Statistics facts. Y hat at Y hat HQ. There's a company out there selling software called Y hat software. We call it a hat. I love it. It's got a little hat on it. Statisticians don't have much going for them. We'll get that hat thing. Y hat is our estimated response. So that's what we figure something's going to be. Beta 0 is our intercept and beta 1 is our slope. We don't know what our error term is. So, here we deal with residuals. Our actual minus our estimate is our residual. Really what we're looking at here is the absolute value. We're just looking for the difference between them. The difference between our estimate and the real one is called the residual. That is critically important as we go forward. An enormous amount of the rest of the semester is on the board right now, folks.
So the first equation you showed was the actual,
Yes.
the second one is the estimate?
This is the simple regression model. This is the mathematical model. And when we fit it to our data, we get this type of equation in this format. So, here's our illustration. Here's a scatter plot of data that we fit a regression line to. This is debt payments and income. So, given a certain income, we fit a line to it, so now we can estimate, right? This line is our best estimate of debt payments for certain levels of income. So, let's say someone has an income of $85,000. How would we use this line to estimate their debt payments? Go 85,000 and go up to our line, and this is our estimate, about a little over 1,000. Well, our actual data point here is right at about 1,000. So our estimate is high, right? We're overestimating our line. We're close, but we're overestimating a little bit. The epsilon, our error term, our residual, is the difference between the actual and our estimate. That difference right there is our error term. The equation of this line is our y hat equals beta 0 plus beta 1x, where beta 0 is the intercept and beta 1 is the slope. Questions? Bring it down. Critical, critical, critical. A lot of the rest of the semester is on the board right now. It's a big day for you in your statistical lives. I'm excited I get to introduce you to this. It's nice.
So the E, that error term?
E,
is
epsilon, residual.
That's the term that was added on to the first equation.
Yes. Yeah. Because we always know there's some error out here. We always know there's some random error. Our dots aren't going to line up in a perfect little nice line. So we know there's some randomness. We include that E in our theoretical framework because we know that there are things we can't always account for. E is the shadow of things unseen. It is what is existent but not knowable. If I can go back to my philosophy days for a while. Still got the beard. Least squares estimate we talked about last time. Here's the math behind it. The debt payments example, they're doing the math. Interpreting the coefficients. We will get into this more in depth in a moment. For now, what did we want to see more of? Examples. Let's do some. Let's do some. Chapter 14, data. Fire up your computers. Follow along at home, kids. Chapter 14, data. I like Arlington Homes. The fastest way is somebody watching that damn debate. I saw you debate watcher. I don't know who you were. I just saw Donald Trump up here. I'm not sure I can go on. I've downloaded Arlington Homes, Executive Compensation, and SAT. I'm going to start with those. I know I like Arlington homes, so I'm going to start with this one. And I'm going to go ahead and download this COL. I'm going to delete this column. This COL, I'm going to go ahead and delete this column. We're not going to use that. So to simplify things, here's our Arlington homes. We have 4 rows of data here. Here's the sales price of homes in Arlington. Here's the square footage of those homes. Number of bedrooms and number of baths. You can have half baths. You've never bought a home before. It is important when you're working with data and you're doing math, it is easy to get into the habit of open your file, jump in, start doing analysis, blah, 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 blah. Look at your data. I will stress this over and over and over again. Look at your data. What is it telling us? Before we start doing math, just read the damn numbers. What are we working with? What is it telling us? What's the first thing that pops out at us about homes in Arlington? They're expensive. Arlington's a nice neighborhood. 40,000, 50,000, or 500,000, 800,000? They're expensive homes. 2,000 square feet, 1,900 square feet, they're big homes. Arlington's a nice area. So maybe we're working for a real estate agent who wants to know what would be our dependent variable here. What are we trying to predict? Yeah, we're trying to predict how much a home will sell for. We're trying to predict how much a home will sell for. So if somebody calls up your real estate office and says, hey, I got this house in Arlington, I'm thinking about selling it. What do you think the market's going to, what do you think I'm going to get? What do you think I'm looking at here? Where do you think I ought to set the price? Because when you're selling a house, you decide what you're going to sell it for. Where do you think I ought to set this price? Am I too high or too low? Well, it depends. What might the determinants of the price of a home be? How big is the house? Square footage. How many bedrooms? How many baths? Are there other things that aren't on here that might matter for the price of a home? Yeah. There's things we haven't taken into account. Is there a pool? What school district is it in? How close is it to downtown? How close is it to a metro line? Is it a 4th story walk-up? Or a ground level? Is it over a florist? Or a fish shop? There's a difference, believe me. One smells like flowers and one smells like fish. What is nicer? So, look at your data first of all. What is this telling you? This is a nice neighborhood. So we might want to do some correlations. Oh, wait, sorry. Better? Alright, so we might want to do some correlations. We might want to correlate the price of the house, comma, with square footage. What would we expect to see here? A positive, strong correlation, and indeed that's what we see. We could repeat this calculation for beds. Strong, but not as strong. And baths. Very strong. I'm going to take these and I'm going to take off a couple decimal points. Some of you on your assessment said that I go too fast in Excel. You got to shout out. All right. Hey, what'd you do there? Hey, what'd you do? Stop. Wait. You can stop me. It's all right. You should. Because if you're thinking it, 5 other people in the room are thinking it too, and they're too chicken to say anything. Be bold. Be brave. Stand up. Tell me to do it again in Excel. Oh well. It's all right. It's what we're here for. If you don't understand what I did, you can't learn. If you can't learn, I don't get paid. I like this correlation, price and square feet. That's pretty strong, pretty positive. All these are in the direction we think they are, right? All these make sense. If one of them didn't, we would want to stop and look at our data. If one of these turned out weird, we would want to do some investigation. What's next? What do we do next?
Scatter plot.
Let's scatter plot them. Let's scatter plot price and square feet. I highlight those two. Insert. Scatter plot here. What does my graph have? Look. What does my graph have that all graphs need at all times, with no exceptions? It has a title. It has labels on both axes. All graphs must have these things, or they're bad. Bad charts. Bad charts. Don't make bad charts. End the madness. I see too many bad charts every day of my life. The cycle stops here. Good charts. Only good charts. Good feelings, good people, good charts. I love the t-shirt. It's Louisville Craft Beer Week, and or next week I think is Louisville Craft Beer Week, and next Saturday is the Beer Fest at Louisville Slugger Field. One of the seminal events on my annual calendar. And I love their logo. Good people drink good beer, bad people drink bad beer. Good people make good charts. Bad people make bad charts. Don't make bad charts. Okay, so we have a scatter plot. And it shows us our rough pattern here of a positive relationship, which we would expect, in which our correlation coefficient indicates. Do we have any outliers? Maybe a couple here. A couple doesn't look that bad. Looks like we have a pretty good pattern here. What's next? Trend line? Let's fit a trend line to it. I click on my data sets. I right click. I go to add trend line. I want a linear trend line. And as we do every time, we display the equation and we display the R squared on the chart down here. Yep. I highlight, click on one of my data points. I right click. I go to add trend line. We're going to leave this at linear. And down at the bottom, I click display equation on chart and display R squared value on chart. Then I can close this. I can click the little X here, here. I can grab my equation if I like and drag it somewhere a little more readable. On your screens over here, it looks like most of you are following me. So, what does this look like? Slope-intercept form. Here's our regression equation. In this regression equation, what is y?
Dependent.
I'm sorry? Y is dependent. What's our dependent variable? What are we predicting here? Price. What is our intercept? 166? What is our slope? 0.0034. Well, who cares? So what? Big deal. What's x? What are we using to estimate here? What's our variable? Square feet. So can we use this equation in our line to estimate the square footage of a house? What if we have a house in Arlington that's 2,000 square feet? Can we estimate the price of the house? Y hat equals beta 0, which is 166.33, plus 0.0034 times what? X. What's our X? 2,000. Help me out, somebody.
172.8. 172.8.
17228.
172.8.
Yeah, 172.8.
Would that be
172,800.
172,800. Because we're in thousands.
Can't be right.
would that be flipped around? Because if
Yeah.
we're going Y, that'd be the square footage, and the X would be our sales price.
Yes. Yeah, it's done backward. I'm sorry. Watch how I fix it. No? Yeah, this is doing it backward. This is predicting square foot by sales price.
So it's 332,000.
See if we can. Ah. That's better, isn't it? Redo. Sorry, I mixed up my X and Y there. I'll make worse decisions than that. Our price, Y, equals, I knew that that Y-intercept was way too low. What's my Y-intercept? 171331 plus 179.14 times X. Our X is still a 2,000 square foot house. So somebody help me out, what's our house price here? 179.14 times 2,000 plus that.
529,611.
529,611.
Yeah.
Can you show us again how you changed your chart so quickly?
Yeah. When you have a scatter plot like this, I right-click and go to Select Data. And notice how it only has one series over here? Because there's only one data series. So this data is defined by, if that's highlighted and I click Edit, X values and Y values. So I just swapped the X and the Y. Here it's telling me that my X's are here in square footage and my Y are prices. And before they were opposite, so I swapped my X and my Y.
Will we have to be on the lookout for that?
It doesn't hurt. Yeah.
Like I know you mentioned you kind of knew something was off because the X value was so
Yeah.
low at first. Should we be looking for like a big X value?
Well,
generally?
it's not a big X value, but let me show you how we interpret these. I love it when you guys lead me straight into the next point. Let me show you how we interpret these. If instead of 2,000 square feet, what if our house was 2,001 square feet? Now what is our house price? Mathematically, what have we done? We've raised this number about 1, right? So instead of 2,000 of these, it's 2,001 of these. So adding 1 square foot to our house has added how much to our house price? $178.09.14. Algebra whizzes in the room will note that I'm talking about the definition of slope. So how do we interpret this $179, or this 179? How do we interpret this coefficient of slope? Speak it up.
Price per square foot.
Yes. Perfect. Flawless. Gold star. Nice job. The rest of you had it too, I just couldn't hear you. For every additional square foot of home space, price goes up by 179.14. Bigger your house, more expensive by this much. Useful bit of information to know, isn't it? In theory, what's a 0 square foot house? 171, but of course there's no such thing. So that's how we interpret these coefficients. We interpret this coefficient as price per square foot.
And do we only interpret within our data?
Oh yeah. Well, we can interpret this anywhere. So if somebody comes to me and says, hey, I have a 2,000 square foot house, I can say, you know, this is roughly the cost. That's a valid, we can do that. That's what we're here for. We're estimating. We're estimating. So let's say that's the estimate of the house, then the realtor actually goes out and sells it, and it sells for $525. What's our residual? $4,611, yeah. That's our error term, that's how much we were off by. Our estimate was off by a little bit. It's not that bad, happens to the best of us. Can I make a formula in Excel now?
Can I see just look that data one more time to get to 179, 114?
That. You gonna do another one? You gonna do another one from scratch?
Yeah.
Sure.
All right, let's do another one from scratch. So, price and number of bedrooms. Highlight these two things. Insert a scatter plot. This time, we're going to make sure these go the way we want. Right click, select data, edit, so that my price is up here in my X value. Tell you what, I'm just going to get rid of these. Well, getting rid of them. And I'll click this little button here next to this. What do I want on my X value? What's my X? For X, I'm going to click this box. X is my bedrooms. Highlight all my data. Click the box. And for Y, I want price. That's my Y variable. Remember our Y hat? That's my Y variable. Now you're getting there. Ty Merca, nice graph. Ty Adams, nice graph. Loxley, nice graph. Good. Good. We right click, add trend line, turn on our equation in R squared. Here we have our regression equation. How much is an additional bedroom in my house worth to me? $66,000. Every additional bedroom adds roughly, on average, $66,000 to the value of my home. Useful number to know. What's the starting price, the minimum price of a theoretical home with no bedroom? $300,000. Yeah.
What's R squared again?
R squared is a measure of the goodness of fit of our line to the data. R squared measures how well our regression line fits our data. I will get into that in more depth later. I will discuss R squared at painstaking depth. Mortifying, stupefying, sleep-inducing death. You'll weep R squared before I'm done. You think I'm kidding? Not at all. So we could write an equation here, right? We could use this to say we could estimate price based on bedrooms, right? Price equals 300,114 plus number of bedrooms times $66,661. Right? There's the price of our house. We can estimate those like that. Everybody see that dark magic I just did? Evil. Not just evil. Evil. We can use this to estimate. That's how our regression, this is a simple regression model. We can use this to estimate. The more years a bourbon spins in the barrel, typically the more expensive it gets, right? We can fit a line to it, and we can estimate for an 8-year-old bourbon, we can estimate roughly what we think we should pay for it. And if it turns out that we pay more than that, what would we say about that 8-year-old bourbon? It's maybe a little overpriced to the market. If we find out that we're paying a little under that when we go to our favorite store, what might we say?
Great deal.
It's a good deal. That's a value. Regression line, forecasting and estimating. Questions? Yes?
So, are there ways to put the bathrooms in as well to calculate? Okay. Getting a little bit.
Easy, easy. Of course there is. Yeah, of course there is. We'll get there. Questions on this? Outstanding. Nice work, everyone.